we're going to be looking at quadratic applications again, but specifically at vertical motion problems. So this is the equation that we're going to be using today. And there's two things that you need to plug into your equation: your initial velocity and your initial height. So let's take a look at this first problem. You are standing on a bridge over a river, holding a rock 36 feet above the water. You toss the rock up with a velocity of 20 feet per second and watch it hit the water. Write a function which models the height of the rock over time. So there's two things that we are given. 36 feet above the water, which is the initial height. So this is S naught. V naught is your initial velocity, and that's your 20 feet per second. So these are the two numbers we're going to plug into this equation when we're writing the equation for this function. So we have h of t, the height, is equal to, so it's always going to be negative 16t squared. We're adding the velocity, which in this case is 20t, plus the initial height, which in this case is 36. So this is the equation I'm going to be using for this situation. Now to the graph. Again, we start off by labeling our axes. So we know that it's a function of time, so time is our x-axis, and it's in seconds because it says feet per second. And then over here is height, which is in feet, because they've given us feet up here. So now we're going to graph this. So back to our calculators, let's start off by clearing the memory. So second plus 712. Make sure our calculator is starting off clean. And we're going to go to y equals and type this, our equation, into our first y1. So we have negative 16x squared plus 20x plus 36. So every time we see t, we're replacing it with an x. Let's go to our window. So just like yesterday, we're going to start off with 0 to 10 and 0 to 10 in both our x and our y. We're starting at 0 because we can't have a negative time. So we're only going to be looking at the positive numbers. So let's graph this and see. So right now, as you can tell, we can see the bottom part of this parabola. So our x's are good, but we need to increase our y. So let's go back to window and increase our y. So we're only changing the y max. We're going to add a 0 and make this 100. So now. And then now we can see the entire function. Great, so let's now narrow it down. We can zoom in a little bit. So instead of having our x's be 0 to 10, why don't we make it 0 to 5? And that zooms in a little bit. We could also probably zoom in on our y's as well. So let's cut our y max in half as well. So go back to window. Instead of 100, let's say 50. So now we're 0 to 5, 0 to 50. And for my y scale, instead of going up by 1s, let me go up by 10s, just so it's easier to label. And now this is a graph that I can plot. So if it's going up by 10s, 10, 20, 30, 40, 50, this is starting right in between 30 and 40. Down here, this is going up by 1, 2, 3. It hits somewhere in between 2 and the 3. So this is a nice sketch of my graph. And now, just like yesterday, we have to find our important points. So we're going to find our maximum as well as our 0. Let's start off by finding our max. So second calc, no, max, we're going to go to the left side of the maximum. Enter. Right side, enter. Guess, enter, and we should get a point. So we have 0.625 and 42.25. That's my maximum. Now for my minimum, my 0, I'm going to go to second calc number 2, which is 0, and left bound of the 0. So again, my 0 is right here. You want to go on the left side of the 0, and then on the right side, so it's off the graph. Press enter again. We get a 0, which is 2.25, comma 0. Which is right here, 2.250. Those are my two important points. Using these points, we can now answer all these problems. So for our domain, we're going from, we know it starts at 0 until the biggest x value, which is going to be 2.25. My range, again, starts at 0, goes all the way up to the maximum, which has a y value of 42.25. When will the rock hit the water? That means it's going to hit the water right here at the 0, which is at 2.25. And don't forget your units, this is seconds. What is the maximum height? The height is our y value, so we're looking for what is the y value of the maximum, which is 42.25. Height is measured in feet, so this is feet. When will the rock reach its maximum height? So this is asking you when, which is time. So this is your x. And so your x value is 0.625, again, seconds for x. So that's problem number 1. Let's look at number 2 now. Suppose you just release the rock and let it fall to the water. So this time, if we just release it, there's no velocity. So what happens is now our function doesn't have that v anymore. It still has negative 16 t squared. But now there is no v. We're just going to go straight to plus 36. Because we're still standing on the same bridge, so we're using the same initial height from the last problem. Now let's graph it. So just like before, we have time in seconds, height in feet. And now we're going to plug this into our y equals negative 16x squared plus 36. This is now my y1. Let's just graph it and see if we can use our same window from before. It looks like we can. So we're just going to use this to draw our graph. So we have 1, 2, 3. It hits somewhere between the 1 and the 2. 10, 20, 30, 40, 50. This is somewhere 1, 2, 3 between the 30 and the 40. And so this is my graph. Okay, so let's find again our maximum and our 0. So second calc max, we're going to go on the left side. So in this case, our left side is going to be off the graph. You're not going to see it. So when you move over to the left, your graph might actually move a little bit over. That's okay. So left bound, right bound, guess. And this e to the negative something, this is scientific notation, it just means 0. So this is 0, 36 is our maximum. Our 0, second calc 2, now we're going to go to the left side of the 0. Right side of the 0. Enter. We have a 0 of 1.5, comma 0. So looking at this, our domain goes from 0 to 1.5. Range goes from 0 to 36. When will the rock hit the water? It hits the water right here at the 0, so 1.5 seconds. What is the maximum height? Is our y at the maximum height is 36 feet. When is our x value for when it will reach its maximum height? It will be at 0 seconds because it hits it right at the very beginning. Makes sense because it doesn't ever get higher than when you released it if you're not throwing it up. Okay, number 3, how would the function change if you threw the rock toward the water with an initial velocity of 20? So before you were throwing it up in the air, now you're throwing it towards the water. So our function, we still have the negative 16t squared, but this time if you're throwing it downward, instead of having a 20, this is going to be a negative 20 for your velocity. All right, 36 is still 36. So if you're throwing it down instead of up, your velocity becomes negative. When will the rock hit the water? So let's graph this. We're changing the function, so it's negative 16x squared minus 20x plus 36. When we graph it, we're looking at when it hits the water. So we're looking for the 0. So let's do second calc 0. Left side of your 0. Right side is 0, so off the graph, yes. We have a 0 of 1 comma 0, so 1 second is when it would hit the water.